Second talk will be given by Professor Rajaram Nityananda. He is an ICTS endowed visiting professor here. And he's going to tell us about light scattering and quantum mechanics. It's really about the Raman effect. He was actually spent 25 years from 1975 to 2000 as a faculty member in the Raman Research Institute, so eminently qualified to tell us all about Raman effect.
Okay, we heard earlier in the day that this was going to be the day of quantum information. So all good things have to come to an end. And we are now still going to be quantum, but the abstract basically says what I intend to do. So light scattering is all about fluctuations. So even the original Rayleigh calculation of the blue of the sky, where he just added up the intensities from different atoms, implicitly assumed that the fluctuations were Poisson, that these were uncorrelated. And the best way to see that is to compare the attenuation of our own atmosphere, which is like 10%. So 10% gets scattered. But if you took the same number of atoms in 1 meter of optical fiber, some ridiculously small percentage would be scattered because, of course, their locations are highly correlated. And all the scattering is really in the forward direction, the refractive index. Okay, so it's Smoluchowski who really brought in the correlations at the critical point. And then there are other kinds of fluctuations that also give rise to scattering. So, for example, orientational fluctuations of complex molecules in liquid, and that's what attracted Raman, in fact, to the subject. Legend is that he looked at the blue of the Mediterranean, and unlike other people, he always carried Nicol prism, maybe a small direct vision spectroscope with him. But in any case, the other kind of fluctuation, closer to our theme of light scattering with frequency change, is originally pioneered by Brillouin and Mandelstam, that once the theory of specific heats kicked in, and particularly the Debye version, where you had these moving density fluctuations, then it was one step, which both of them took independently, to say that you would get a frequency shift, could have either sign, depending on whether the wave was running away. And it was tightly correlated, of course, with the angle. And in some sense, the whole business of light scattering with frequency change should have started here. But this is a very small frequency change of the order of the velocity of sound over the velocity of light, more like 10 minus 5. So in that sense, this didn't directly result in the developments that we're going to talk about. Now, the refractive index might seem to be a very strange place for very fundamental physicists to start thinking about. But indeed, in the 20s, this is exactly what happened. What you see in that formula, if you ignore the summation sign and ignore the F, is just the contribution to polarizability or the refractive index from a single classical oscillator, so-called Drude formula. But what people found they needed, by that time, experiments, especially say on sodium vapor. So for all practical purposes, you have just one electron over there. But of course, Bohr had told us, an experiment had told us that the same electron had many absorption frequencies. Okay, so it's as if it developed a split personality, and you had these weights, oscillator strengths, Fs, adding up to 1, and you had a sum of many of these terms. Okay, and people who were trying to understand it, of course, you didn't have full quantum mechanics by this time. And one of the people who started thinking about this was none other than Kramers. So he generalized this formula a little bit in a paper in Nature, where he said, okay, the atom doesn't necessarily have to be in the ground state. It could be in an excited state. And Einstein had already introduced the world to the concept of negative absorption or stimulated emission. So Kramers had a generalization of this formula in which some of the F's would be negative. Okay, but there was still no physical basis for that. But curiously, the F still added up to 1. So as a point of history, we usually derive the sum rule by taking commutators and so on, but it actually predates quantum mechanics. Maybe one way to think about it is to just go to very large frequencies, and then you ought to recover the formula for a single free electron, right? And therefore the F's have to add up to 1. And yes, Kramers also had the advantage of knowing the Kramers-Kronig relations, which sort of dictate the general form of the relationship of absorption with dispersion. And of course, in these simple atomic systems, the absorption just consisted of these discrete frequencies. Okay. So then, and the dates now become important. So in January 1925, he teams up with Heisenberg to try and give a physical basis for all this. But it's really, really a case of having lost something and looking for it under the lamppost, because the only source of illumination which they had at that time was the theory of action angle variables for multiply periodic classical systems. Okay, and since there were many frequencies, they invented a hypothetical system which had many action variables and many angle variables. Okay, but they also introduced an ingredient which predated them by a couple of years, and this is due to Smekal, that scattering can occur with frequency change. Okay, and Smekal's reason is kind of interesting. He was building on Einstein's work on spontaneous and stimulated emission, both of which were necessary to have thermal equilibrium between a pair of levels. And he said, look, we also want thermal equilibrium with the translational degree of freedom. And so he considered scattering processes in which there was exchange of energy and momentum between the quanta and the moving atom. So frequency change was very natural in this framework. Now you might say, why is this such a big deal, right? Conservation of energy and momentum. Well, this was a very, very turbulent period in the history of physics. So no less a group than Bohr, Kramers, and Slater had actually written a paper on this general theme, which decided to give up conservation of energy and momentum. The thing that, and the reason why they took the desperate step is because they did not want to take quanta literally. Okay, this looks very strange. That Einstein and Smekal and so on were saying, well, here are quanta and let's work with them. And of course, this group, which was trying to understand something different, like dispersion, took this very desperate step. One fortunate consequence, side effect of this collaboration was that it put Slater, who was a kind of innocent bystander, completely put him off, and he went on to a brilliant career in the quantum mechanics of atoms, molecules, and solids. Now, the Kramers-Heisenberg paper sets up this fictitious classical system, but you will not find a mention of quanta in this paper. What they really do is that they have these action variables and angle variables. I hope that's your idea of entertainment, because that was what you were promised. But anyway, they have these things, and then they set up a perturbation by an external field. So their model is that the atom has these dipoles, and the dipoles have their own characteristic frequencies. They can radiate, and they must, because naturally they wanted to explain the most basic fact that atoms can radiate at different frequencies. But the strengths of these dipoles are expressed as functions of the action variables in Fourier series, so that they can radiate at a frequency and its harmonics, because these are nonlinear oscillators. Okay, a pretty elaborate model. I won't go into the details. And when they pushed it to its logical conclusion, after some virtuosity with canonical transformations and so on, they were able to obtain both scattering without change of frequency, which is essentially the dispersion of the refractive index, and scattering with change of frequency. Okay. So I'd like to show you some of the results. Okay. Someone was remarking that we didn't have enough German, right? So you can see a little German on the top left. It's their derivation of the formula, which consisted of two words. Man schreibt, one writes. Okay. So this is the quantum formula. You see a QU, right? You see a QU here. And I have spared you the classical formula, which is much more complicated. But basically, what they did and what they explain in a single long sentence is that from this classical formula, guided by the correspondence principle, and in order to be consistent with what is already known about dispersion, we write. And this is what they write. Okay? This is just equation 27. And this is for the case where you have scattering without change of frequency, because you see just the same frequency over here. And then many equations later, they write down something for scattering with change of frequency. So you see nu minus nu star, and you also see nu plus. This is nu again, of course, which is the same, the refractive index thing. Well, since we are all celebrating an event, that's the event which happened 6 months later. Okay, so this was Heisenberg alone, and he probably needed to be alone, right? Because after doing this very complicated exercise, which is very heuristic with Kramers, he probably went away to, think by himself. And I think, again, Shankar Das Sharma mentioned that very few people understand this paper, and I belong to the same group who do not understand the paper. But I did understand the introduction of the paper, okay, because he says quite clearly what are his motivations. Okay, he gives up action angle variables. And the example he gives is an atom in crossed electric and magnetic fields. He says, we don't know any action angle variables for this system, but it's as good an atom as any. The other thing which he gives up is dipoles. So basically, he took his work with Kramers and decided to remove various unnecessary ingredients from it. And his argument is interesting. He says that, in principle, radiation can occur in higher multipoles, like quadrupoles, which require x square. He doesn't mention magnetic dipoles, but I'm sure he knew about them. So that would have X and V. And following the reasoning of the earlier paper, every one of these now has to become a quantity with two indices, okay? Because that already happened in the Kramers-Heisenberg paper. And that happened at the step where they did this quantization, where J went from being a continuous variable to being multiples of Planck's constant. And derivatives became differences. So that's how they got that formula. Okay. And of course, the rest is history. He created matrix mechanics. And at least one person, in another country understood what he did, and that was obviously Dirac. Okay. That's his November 1925 paper. But what concerns us more is a later paper he wrote in 1927, okay, which is on the quantization of the interaction between light and matter, which is exactly the same problem considered by Kramers and Heisenberg. And here is his formula. And it's sort of interesting that he says this is identical with Kramers and Heisenberg's result, which I'm offering you again for comparison. It doesn't look identical for a couple of reasons. One is, of course, Dirac's legendary powers of expressing himself very briefly. And the other is that, perhaps driven by history, Kramers and Heisenberg separated terms in which the transition was upwards and the transition was downwards. So they got several different cases, all of which are unified in Dirac's formulation. If you have ever read Dirac, you will know that you have to very carefully count the primes, okay? So in this formula, you see a J prime, a J double prime, and, right? And so what's going on here is just of course, by this time, quantum mechanics in essentially the form that we practice it today had been created. And all this is actually before any experimental evidence of these processes, the so-called Raman effect, which we'll come to in a minute. But as a side remark, one might well imagine that all this agonizing about photons and what they are should have ended at this point, because it's all written out. He's removed the oscillators from the atoms and put them in the right place, which is the electromagnetic field, and just set it all up, right? But as a personal experience, well into the late 20th century, I've listened to lectures by very distinguished physicists, practitioners of optics and spectroscopy. Maybe because it was a general lecture, they were being a little informal, and at the end, both of them ended by saying they wished that we didn't have to deal with these photons, and hopefully something nice will come to replace it with something closer to the heart's desire. So this is, I think people still agonize about photons, but maybe one should just go back and read this paper. Okay, so now we come to the experiments. Okay, so I've summarized it by saying that these experiments occurred in two cities, Calcutta and Moscow, but unfortunately only one Nobel Prize was awarded. So in Calcutta, starting around in the 1920s, C.V. Raman launched a kind of attack on this problem of light scattering. His motivation actually seems to have been that you would learn more about the nature of light and also about the nature of molecules. Okay, so they really and they chose liquids. Okay, for very practical reasons, liquids can be purified readily, and whereas in Moscow, about the same time, Mandelstam, along with Landsberg, decided to study light scattering in crystals. And of course, he already had this concept that you will see frequency changes, okay? And they chose quartz and calcite. Now, actually, the equipment in Calcutta was much more primitive than that in Moscow. For most of their work, right? I said that they saw scattering with frequency change, but this was not with a very monochromatic source or a full spectral resolution in the detector. They in fact just had complementary filters, something which would only transmit violet, which would fall on the sample, and then they would look at it through a green filter and do this for a large number of liquids with a large number of students, right? Now, in the case of the Moscow group, around the same time, we won't quibble about 3 and 4 days this way and that way, though people have done that. They of course had a much more standard setup, and also this clever trick of using a mercury lamp and then using mercury vapor as a filter in the scattered beam, so that you attenuated the incident frequency, and therefore you are better able to see the scattered frequencies. And in these crystals, they found shifted lines, shifted both ways, depending on temperature, okay? And they also compared these frequency shifts with known infrared behavior of these crystals, which had been studied. A much more difficult study, because those infrared frequencies corresponded to 9 microns or 20 microns, which is not that easy to study, right? And of course, they might have been inspired by the old prediction of scattering by sound waves, but they very quickly realized that what they were seeing was at a much higher frequency, and it corresponded to the infrared, what are called residual rays, or basically infrared absorption frequencies, which had been seen in these crystals, okay? And they went to, Raman went to Nature, they went to Naturwissenschaften a little bit later, and they were a bit slower, so by the time they wrote, they also added a paragraph saying, this may be related to what Raman and Krishnan have been saying, but they don't give enough details for us to make any statement, okay? of course, Raman has been sort of waiting for this day. So he went to the press the same evening and then went to Bangalore in a couple of weeks, gave a lecture with demonstrations. It was called The New Radiation, wrote it up, published it in the Indian Journal of Physics by 31st March, sent out, I mean, by one account, 2,000 copies all over the world, right? So clearly, he won at least the public relations battle, okay? There's a later follow-up paper, not very late, May 1928, which gives all these details from the Moscow group. And they really focus on just these two crystals. Whereas, of course, the Raman group study a huge range of liquids, and they make the point that this is the universal phenomenon, okay? So this is not so much the Raman effect, but the effect that Raman seems to have had on his surroundings. First of all, some people, like the American spectroscopist R.W. Wood, said, oh, this is one more nice confirmation of the quantum theory, right? There was already the Compton effect. So at least in those times, although quantum mechanics had already been around for 6 or 7 years, but I think what really seems to have caught the imagination of the whole world, in contrast to the Russian work, is that this could be used to study the vibrations, mainly vibrational transitions of organic molecules. Germany, in fact, was, of course, probably the king of organic synthesis in those days. And the ultimate sign that one has arrived is if your work is covered in one of these handbook series in those times. So here is something from, yes, The Structure of Matter in Monographs, edited by none other than Max Born. See the irony, we'll see the Born-Raman interaction later. And James Frank. And the author, Kohlrausch, himself carried out a number of experiments and gathered all the data. This book is in the Raman Institute library, and I asked the librarian to give me a copy. He didn't give me a copy of, this is the front page, but not the cover. Because on the cover, someone, no prizes for guessing whom, had struck out the Smekal part, okay? And the beauty, of course, was that this was all in a very accessible region of the spectrum, okay? Now, there's a later paper by Raman and Bhagavantam, which Bhaskaran mentioned, that there's a selection rule for the rotational Raman effect, which you can interpret if you send in something with one circular polarization and it comes back with the, having changed the direction of its angular momentum, right? And then the selection rule says that the rotational quantum number of the molecule will change by 2. Then, in some sense, you have verified the spin 1 associated with the photon. Of course, they were right, but where, they claimed more. They said that, this absolutely proves the quantum nature of light. So, on the one hand, while Raman was not a quantum physicist in the same sense that someone like Mandelstam was, he was very eager to make an impact on the development of the new ideas, okay? Of course, it turns out that this claim cannot be completely substantiated because you can derive the same selection rules from the semi-classical theory of radiation. And in fact, the story will probably be repeated when the first people manage to detect gravitons. Well, people will say, detect excitation in some bar. We'll say, yes, but we could explain that by a classical gravitational field interacting with the bar, okay? So it's all very well for Dirac to write down a formula for inelastic scattering of light and say the rest is chemistry. But chemists need something that they can think about and work with. And that was given in 1935 by George Plakjek. I won't go back to the Kramers-Heisenberg or the Dirac form of the formula, but all you have to know about it is that for forward scattering on the refractive index, you start and end with the same state. And for scattering with change of frequency, you start at some state and you end at some other state. So the first one is, of course, called polarizability or refractive index, whatever you like. So it's very logical to think of that as some kind of matrix of which this is the diagonal element, and then the amplitude for Raman scattering is the off-diagonal element connecting two different states. And of course, in Heisenberg's way of looking at quantum mechanics, which is, of course, the way that's prevalent today, the diagonal elements describe expectation values, and the off-diagonal elements describe fluctuations. Okay, so the Planck formulation is based on the much more intuitive notion that you have this molecule. It has a polarizability when you put the nuclei in a given configuration, in a given position. And then, of course, that's a very classical way of thinking, but the positions of nuclei are not classical. They are subject to quantum mechanics. So then polarizability becomes, you can compute it as a function of the coordinates of the molecules. And then when you quantize those coordinates, you'll get vibrational levels. And so all you need to do is to parameterize the variation of polarizability with nuclear coordinates. And that's a much more intuitive concept than just loads of matrix elements and so on. And that's pretty much the formulation which most chemists use. Okay, so basically it's a fluctuating polarizability which sort of takes you back. For example, if the dipole moment of something is the polarizability times the incident electric field, and if the incident electric field has some frequency and the polarizability also fluctuates at some other frequency, it doesn't need much to see that you will get sums and differences. Okay, I mean that was known to radio engineers probably well before all this. Okay. So now I'm moving to 1945. This is something from the proceedings of the Royal Society. It's a comparison of theory and experiment in the Raman spectrum of rock salt. Okay, that's what the authors called it. This huge, the thin line is the experiment, but you can ignore this huge peak because in spite of all the precautions, a lot of the mercury vapor line is coming in. So all these components with small frequency shift, are drowned out. But you clearly see a continuum with bumps on it in the experiment, and you see a continuum with bumps on it in the theory as well. Okay. What's a little unusual about this is that the experiment was done in Bangalore by R.S. Krishnan, who is not to be confused with the K.S. Krishnan, who worked closely with Raman in the period that the Raman effect was discovered. So this is much later in the 1940s in Bangalore. And the theory was done in Edinburgh, right? And both the theory and the experiment required heroic efforts, okay? So in the case of the theory, there's a selection rule for a crystal with the symmetry of rock salt. And you can sort of see it intuitively from the way that Planck thought about it. You have this optical vibration where the two sublattices are moving in opposite directions. But clearly the polarizability is going to be the same whether you move it to the left or right. Okay? So you will not get a first order Raman effect. The polarizability expanded in terms of these normal coordinates will start with some quadratic term. And therefore, you will get a second order Raman effect. Okay? So which now, according to Max Born, right, who's the first author, and to use Michael Berry's terminology, the alpha male of lattice dynamics, okay, he therefore had to ask his students and their assistants to literally compute all pairs of phonons, if you like, right, whose frequencies added up or subtracted from the Raman frequency. And this had to be summed over all branches. So there are 6 branches of the spectrum. So you can see that was a pretty heroic effort. It has to be done over the whole Brillouin zone. So one sidelight is that in those days, I get the impression reading these papers or even Chandrasekhar's papers that a lot of the computational heavy lifting had to be done by women. So you have Mary Blackburn and you have Joan Smith, who was not an author, but she's thanked. Okay? And to add insult to injury, they were called computers. not even computesses, but computers. Okay. So in any case, why would Born, want to put in so much effort to confirm his theory of lattice dynamics? And the experiments were equally heroic, by the way, because it's a very weak second-order spectrum, required huge exposures, great precautions. I'm old enough, actually, that as a very young student, I've been shown by R.S. Krishnan around his Raman scattering lab. Okay, so if you want a connection, that's there. Okay, so the real point of this example is there in the abstract. Okay, the results show us that Raman's attacks against the theory lattice dynamics are unfounded, because Raman had his own theory of lattice dynamics. Okay, we won't go into why he was misled, but on the experimental side, one misleading circumstance was that the photographic plate is nonlinear. So you have something with peaks. The peaks may well look like sharp lines, and so he came up with an explanation which had sharp lines. Okay, actually, Born also seems to have missed one point here. He makes the point that this joint density of states for any pair of phonons has sharp maxima, and in fact he uses it to motivate an approximation that it's not enough to have the energies, you also need these matrix elements. He said we'll just evaluate the matrix elements at these maxima, okay? But they're not really maxima, they are of course Van Hoove singularities, right? But with the numerical resolution they had at that time, they probably didn't see it. You must have just seen a bunch of very Gaussian looking curves, okay? They, and I suppose it's Max Born who goes on to say that it's nice to see that Raman's own pupil, R.S. Krishnan, has now given results which show a continuum and which contradict his theory. Okay. Now, of course, if you think Born is being rude, I can assure you that Raman in his writings was equally, if not more rude. Okay, writings and lectures. Again, I have personally, I'm old enough that he was asked to inaugurate a conference on crystallography. So he went to the blackboard and wrote down his theory of lattice dynamics. So it was clearly very dear to him. Okay, and this was in the 70s, or 60s. Okay, briefly I'll touch on later developments. The subject didn't end. In fact, it's flourished. Okay, so one thing which was discovered perhaps serendipitously is that you get a very strong Raman signal if your molecule of interest happens to be near the right metal surface. Right means it probably has to be the right metal, and it also has to have the right structure, either nanostructure or maybe some rough things and so on. This is called surface-enhanced Raman scattering. Apparently, the original paper by Fleischmann of Southampton has some 6,000 citations. And even as a phenomenon, it's interesting. I found many different explanations in the literature. Maybe all of them are operating, like the sharp points just concentrating the electric field of the incident radiation. Perhaps the dipole of the molecule, again, having an image dipole and being constructive. Perhaps even the molecule changing its symmetry because it's sitting near the surface. But as far as the users are concerned, they're getting a stronger signal and they're very happy. Okay. Now, the other technique which I learned about from a colleague in NCBS, the National Center for Biological Science, is that you can use resonance. Okay. If you want to highlight a particular molecule in a cell, now that you have tunable sources in the ultraviolet, you sort of tune to that, you light up that molecule, and because you're near resonance, the molecule spends a lot of time. That's that inverse frequency difference denominator which you saw in those formulae, right? And in that time, various interesting interactions with the surroundings can so on happen. I thought they would use a very simplified watered down theory, but she gave me this book by Mukamel, which was very sophisticated. It simply bristled with Liouville space and master equations and so on. I won't, this is actually quite beautiful. I won't say more about it, except that stimulated Brunel scattering. So now when you have a strong laser source, you could have a very distorted wavefront, and it enters the medium, and it creates some distorted sound waves, and they send this back. And to a good approximation, it's the conjugate the time reversal operation beloved of people in quantum mechanics. So it actually goes back through the same distorting medium and comes out in its pristine form. Quite a beautiful phenomenon. And something else, coherent anti-Stokes Raman spectroscopy, which I will not go into, but it's a very clever way of making the Raman spectrum coherent from different molecules. Normally it isn't because they end up in a different final state. But here you use lasers to get it up to some state, really or virtually, and get it back and get anti-Stokes on the way down. So, but what is, I mean, this was cutting edge nonlinear optics at one point, and today, you can buy it in the form of a microscope, and I just took a random abstract from, So anyway, so a little bit on these personalities, right? Extremely confident, the word supreme egotist was used by my thesis supervisor, who was in turn Raman's research student. So I guess you can take it as authentic. And Bond himself, in his initial interactions with Raman, says, I like him very much, in spite of his obvious self-promotion, okay? And Raman, completely a made in India kind of person. Mandelstam spent 14 years in Germany, which could have been very exciting, except that he was in an electronics lab of Braun, who actually did share the Nobel Prize with Marconi. So, in fact, Mandelstam never forgot his electronics and radio physics, was responsible with his associate Papaleksi for making that subject flourish in the Soviet Union. And by all contemporary accounts, seems to have been a cautious person. Apparently, he would keep a paper for a month before submitting it. There's some textual evidence of that, because the Zeitschrift für Physik paper thanks Emil Leontovich for helping us submit this paper. He probably pushed him to submit the paper. Okay, Raman was backed by the Calcutta University. Mandelstam worked at the Moscow State University, but he didn't enter it as the boss. Right? In fact, he had to contend with a large population who didn't even want quantum mechanics to be taught. But I think things looked up for him when he also, the Physics Institute of the Academy of Sciences came up. Right? He didn't get the Nobel Prize, but his stable is very impressive. Okay, Tam and Ginsburg got Nobel Prizes. So did Sakharov or something else. Right? I mentioned Papaleksi, Leontovich, a major pioneer of plasma physics. So nothing to be ashamed of in terms of his impact on later generations. And in the case of Raman, a little different, because all said and done, Mandelstam was working in a self-governing country, and Raman was not. So no question of going and asking for government support, except in the last phases of his life where he didn't want government support. Okay, but he created legions of students. I know no paper where he actually had a kind of collaborator in an equal sense. And they, of course, went on to do many nice things. I met Shobana Narasimhan in the audience, and she coined this phrase, Holy Raman Empire, right? To describe, this legion of people who worked here. So that in brief is the story of inelastic light scattering and some of the physics and some of the people involved. Thank you.
Question? Okay. Can you?
I'm here.
Yeah.
Can you
Go
see
ahead.
me? Yeah. I'm here at the extreme end of the.
Yeah.
Yeah, so you didn't say anything about the controversy about who actually discovered the Raman effect as in Krishnan versus Raman and the missing page from Krishnan's lab notebook. Do you have anything to say about that?
Oh, okay. See, Krishnan was very much the graduate student, and the Nobel Prize Committee didn't catch up with graduate students till, even not for Jocelyn Bell. Finally, I think for the Hulse-Taylor pulsar, they decided to catch up. So that's one thing, right? Raman acknowledges Krishnan. I did not actually show the last slide, but it's kind of relevant to this. Now, Raman is not a quantum physicist, but nevertheless, in this review, which he wrote in 1922, he says we have to quantize the electromagnetic field. You can read the later sentences, right? Not that he knew how to do it, but he said so he had this intuitive approach. Whereas Krishnan, of course, was very well educated, I'm sure even at that time. The other thing is Krishnan has noted that on one of these special days, 7th February, he rushed to his residence and said, we have discovered the Kramers-Heisenberg effect. So he was keeping track of the literature. Okay. So, when people are working together and, doing experiments day after day, I don't think it's a very meaningful question, right? You can ask, it's certainly not true that, Krishnan discovered it alone and Raman took the credit, because Raman had been pursuing this for decades with so many people, right? Now, whether Krishnan should have got a Nobel Prize, you should ask the Nobel Committee. I think the stronger case that Mandelstam should have also shared the prize, but anyway.
I wanted to make a comment over here. I wanted to make a comment and also ask a question. When I went to the United States in the very beginning, I was very young, some very senior professor, very famous professor, in fact, asked me this question that why does everybody in India do lattice dynamics? It's Raman's very subversive influence. What isn't it? Raman was just a name to me. I didn't really know much. So is that true that Raman kind of dominated so much that everybody in India was doing like lattice dynamics up to the beginning of the 70s?
Can I answer that first?
Please.
I think no. Because first of all, Raman's lattice dynamics was wrong. And a couple of his students even knew it's wrong. Like I knew one of them, Vishwanathan, who wrote a thesis based on the standard lattice dynamics. But of course, to please Raman, he showed that the points with zero group velocity, which are essentially zone boundary modes, sort of agree with the Raman thing. And the period where lattice dynamics was very actively pursued in India is much later, well after the period of Raman's influence. And as a graduate student, I used to feel proud that, okay, here is Physical Review, and we have 2 papers by G.S. Varma and 1 more by Balakrishna Agarwal and so on. So anyway, so I think it's completely independent.
All right, I feel better. Right. So lattice dynamics was being pursued, but not because of Raman.
Not because of Raman. Okay, yeah. Because it's something that was doable.
Yeah, got it. So the other thing is that, one field where Raman scattering had a big effect, it's a niche field in condensed matter physics, is inelastic resonant Raman scattering to study electronic excitations. It's not an easy experiment because usually there is a C in the denominator when light couples to electrons. But if you use the band gap as a resonant Raman scattering, then that cancels it. And this has led to beautiful results in understanding very subtle electronic excitation effect in semiconductor and in strongly correlated material. Not many people can do it, but it's a big field for big discoveries. That's where I came across from. My other question, it's a bit delicate, but this is something I have thought about a lot. So the 2 great stalwarts of Indian physics were both in Calcutta, Bose and Raman, in very different ways, right? How do you compare their relative influence on Indian science, in the development of Indian physics? Of course, they're very different personalities.
You're referring to S.N. Bose, right?
Yes, not Jagadish Bose, Satyan Bose.
No, I think the Raman influence is just bigger, no, in terms of the number of. If you think of a person as having a kind of stable, and each of them is again having a stable, my impression is that Raman would outnumber anyone in India, not just S.N. Bose. Right.
It became clear that what Raman had seen were Van Hove singularities, what later became known as Van Hove singularities. How which are singular concentrations of many modes rather than the individual modes that the full theory reveals as being really there. Now, did Max Born ever know that Raman had seen Van Hove singularities? Did he know about Van Hove singularities? And when this became clear, did Raman ever recognize that what he had seen were these kinds of singular concentrations of modes?
Okay, my response to that is that the resolution available at that time, as you can see from that spectrometer trace of R.S. Krishnan's experiment, was not really good enough to show the singularity. right? So it's true that Raman interpreted these photographic spectra in terms of lines. I don't know which came first. His seeing the lines and deciding that, therefore he would only concentrate on modes in which opposite cells move opposite. I don't think he was following the subject closely enough to get into Van Hove singularities.
Did Max
That
Born
would be a kind of anachronistic, so to speak.
and did Max Born ever realize that that's what Raman had seen?
I would not say that because I think if you look at the resolution of those spectra,
Yes, under
it's probably
poor
not good
resolution.
enough because even the fit by Born and Blackburn doesn't have singular from every pair of modes. They just have a kind of Gaussian, right? Which is because of numerical resolution. But the closest I can come to that is the PhD thesis, which was done in the Raman Institute by his student Vishwanathan, purely theoretical thesis, where he used the Born lattice dynamics and then found that the so-called Raman modes, the 24p minus 3, were modes of zero group velocity. Now, zero group velocity will give you a Van Hove singularity, right? D omega by dk being zero. So that's the closest I can. I would not claim that he saw Van Hove singularities. Yeah.
Hi, it's great talk, Rajaram. Listening to you, it seems to me that I think history has been unfair to Mandelstam. So maybe in this momentous year of quantum mechanics, we can start calling it the Raman-Mandelstam effect. I mean, it's not in alphabetical order, I concede, but why not?
Okay. The Russian literature very consistently calls it combination scattering. If you read all the Landau-Lifshitz volumes, you will not see either the name of Raman or Chandrasekhar mentioned, even though combination scattering is mentioned and the limiting mass for dense bodies is mentioned. So yes, I think
Okay.
one certainly could.
Yeah.
Okay, maybe one last question.
It's not a question, it's an explanation. It's that Mandelstam founded one of the two schools of crystal physics in Soviet Union. The other one was of Landau. So it's an explanation why in Landau-Lifshitz it's called combination scattering, not Raman-Mandelstam.
Okay.
Okay, I think we should close this session. So